Okay. So as I said, this is the last little bit of the year. Chezzy made it. Hey, Chezzy. The last couple of things, we're just missing a few little things on here. Okay, so in a continuation of what we were doing the other day on the video, the volume of a cylinder, well, it is base times height. That formula works. If you write down that formula and nothing else, don't answer the question, I'd still probably give you half credit on it. Yeah.
I was late, but I just got here because I had to restart my computer.
Yeah, we heard. So no problem with this formula, base times height, but there's one specific to a cylinder. What is the base of a cylinder? What shape is it?
Circle?
Circle, absolutely. And what is the area of a circle? Pi r squared in there. Pi r squared h. So that formula is just a specific one to a cylinder. It is the same as base times height. It's just we went and replaced the base with pi r squared. Okay. Likewise for a cone, we've got 1/3 base times height. Cat, come on. What is up with you today? So that is going to be 1/3 pi r squared h.
Mr. Reeves, can you move the page over?
Yep, there it is.
Wait, what's the 1/3 pi r squared h for?
That is specifically a cone.
Okay.
So if you don't remember that formula, it's no big deal. It is 1/3 base times height. The base just happens to be a circle, and the area of a circle is that pi r squared business.
Oh, what does it say below the lateral area plus base? I can't read what it says. Like it says pi length, or
this one right here?
No, below that.
Oh, this one here. Pi r l, so the lateral area, plus pi r squared.
Oh, okay.
So okay. So we appear to be missing one column. It looks like we would have 3 more theorem or 3 more formulas left to do, but one of these just isn't a thing. What does it mean when I talk about lateral area? What am I talking about if I say, hey, what's the lateral area of this thing? What would I be talking about?
Like one side?
No, probably not one side, but you're closer than anyone else, so I'll go off of that. The lateral sides are all the sides which aren't bases. So when I'm looking for lateral area, I'm looking for the area of all the things which aren't a base. So in a cylinder, that would be like the round part. If you're thinking of like a can or something like that, that would be where the label is on the lateral side of a cylinder. In a rectangular prism, it's hard to say which side is really the lateral sides, because any of them make good bases and any of them make good lateral sides. But if I were talking about a hexagonal prism or pyramid, it would be all the sides which aren't hexagons. If it's a hexagonal prism, all the sides which are rectangles. If it's a hexagonal pyramid, it would be all the sides which are triangles. Those are my lateral sides. Well, for a sphere, which of course is just a ball, it doesn't have any bases. To talk about its lateral area, all the area on the side which isn't bases, just doesn't make any sense. So that one is just out. This one's kind of a neat formula. It's something that I can't prove, but I can show. Most years I don't. In fact, I've talked about it every year. This year I could actually show it because I am at my house. And I know that there is a big cylindrical shaped lemon in my kitchen. If you guys want me to run out and grab it, I will. Ooh, Baxter's going yes. Is that a nod to me, Baxter? Do you want to see me peel a lemon? We can do this. This is something that my mother used to do when she taught geometry. The surface area of a sphere is a slightly weird formula. It is just 4 pi r squared. And I said that one was slightly weird, excuse me, because the volume of a sphere is definitely weird. It gets a coefficient, gets a number in front, which we definitely do not see a whole lot of. And it is 4/3 pi r. It's a volume, so it shouldn't be really surprising that it's a cubed in there. I know I have a much more romantic approach and feel for mathematics than most people do, but I will tell you, when you get to prove these two theorems in calculus, or these two formulas in calculus, it's kind of neat. Like 4/3 pi r cubed, really? And then you do the calculus and you find out, oh yeah, it's true. The neat thing about calculus is if you know calculus, you don't have to have these things memorized. If you get stuck on a desert island and you need to figure out what the volume of a sphere is, you can derive it. Okay, and that's it for formulas for the year. We have one more theorem. It's going to look somewhat familiar. All right, so I did something very similar to this in chapter 11. And I asked for a nice, easy shape to deal with. And in chapter 11, seeing as we were dealing with two-dimensional things, it was a two-dimensional shape. So this time, on the other hand, I will ask for a nice three-dimensional shape to deal with. What's a nice, easy three-dimensional shape?
Cube.
There it is. I think cube is probably going to be the easiest. I mean, you could do anything. You could do a sphere, you could do a hexagonal prism or pyramid or whatever, but definitely cube is nice and easy. So let's do that. All right. So down here at the bottom of the page, I'm going to draw myself a nice little cube. So something like that looking thing. Boop, 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 boop. Okay, little cube. And I'm going to draw a bigger cube. And okay, what can be said about my two cubes?
Similar.
They are similar, and that was my little joke before when I said I did a kind of similar thing in chapter 11. They, of course, are similar. In fact, any cube anywhere in the world is similar to these two cubes. Let's take some side lengths. For my small cube, what do you want the side length to be?
2.
2. That was what I was guessing. All right, 2. And so all the other side lengths are also
2.
2. You got it. 2, 2, 2. What about for the big cube? What do you want them to be?
9.
9. Sounds good to me. I like 9. 9, 9, and 9. Okay. Okay. What attributes might I be interested in about my cubes?
The proportions.
The volume, the surface area, everything.
Okay. Everything. All right. Volume and surface area for sure. I mean, it's something that we have we have talked about. I heard Allegra say proportions, and definitely that's where I'm going with this. I want to know what is proportional and what is not. But I think really I'm putting these two things together, what Allegra said and what Andrew said, because the things which might be proportional might be the surface area and the lateral area and the volume and all of those good things. Let's start with the easy one. What is the area of the base of my little cube?
4.
I got a 4 in there. What is the area of the base of my big cube?
81.
81. Totally. Interesting. What is the, how about lateral area of my little cube?
8.
It is not.
Isn't it? All right.
Lateral area, little cube. Decided it is not 8.
Twelve.
16.
I heard it.
12.
It's not the 12.
16.
I think it, just because it highlight Zoe's square, like nobody's actually moving their lips when they're speaking to that. Like 16. 16, is that what you said, Zoe? Yes. Okay. It is indeed 16. Remember, lateral area is perimeter times height. The perimeter of the base, 2, 4, 6, 8 times 2, 16. It really just is the area of the 4 squares on the side. So I found the area of one of them, which is 4, and multiplied by 4. What is the lateral area of this guy? Or at least tell me what I would do to find it.
81 times 4.
81 times 4, there we go. So 324, I believe.
Yeah.
Okay. How about surface area of the little guy?
Um,
Is
20.
that 24?
24, there it is. Surface area is lateral area plus 2 bases. Surface area of the big guy.
486.
486. Ooh, 486. Sounds about right. I'm going to add those 2 bases. If I add 1 base, I'm close to 400. If I add another base, I'm close to 480. Seems legit to me. Okay. By the way, I got a little calculator here. Not that we use them in my class, but for the fun of it, if I hit clear, base to base, 4 divided by 81 is this 0.049-ish. 16 divided by 324 is this 0.049-ish. 24 divided by 486 is this 0.049-ish. What have I really, what am I trying to show here?
They're proportional.
Sure, that all the ratios of all the different areas, whether we're talking about base area, lateral area, surface area, the area of one of the faces, the area of the corresponding face, I don't care what it is, any of the areas are going to be in that same proportion. They are proportional. Okay, and in fact, that proportion appears to be 4 to 81, which I feel like we could have predicted with a theorem from chapter 11, which said if 2 things are similar, then the ratio of their lengths squared is equal to the ratio of their areas. By the way, a couple people contacted me about making corrections to the last test. You might be interested in that particular theorem, because that was a largely missed one. Okay. If 2 figures are similar, then the ratio of their lengths squared is the ratio of their areas. Well, I just said that was on chapter 11. That's not what I'm here today to talk about. What ratio do you think I am going to talk about?
Volume.
Ratio of their volumes. You got it. All right. So let's do it. What is the volume of the little cube? I'm kind of expecting Henry to yell this one out first. But maybe not. Allegra, you look like you were lit up for a
I
sec.
feel like that's wrong. Never mind.
Okay. I didn't hear it, so I can't confirm its wrongitude.
The volume of the first cube?
The volume of the first cube.
8.
Yes, it is 8. The reason I thought Henry was going to blurt it out is because I think he accidentally calculated volume early on. I was wondering if he noticed that. All right, but Andrew with 8. Yes, totally. The volume of this guy is 8. The volume of this guy. So sorry you picked 9, but is, at least you can tell me how.
729.
There it is, 729.
I did that without a calculator. I'm a god.
Yes, I will agree with this statement. And I feel like you were also echoed. I think Chesney also both agreed with the 729 and the God statement. Yes? Yeah. He's muted, but he's clapping. All right. Well, what is the ratio of their volumes? Wrote a RV there.
8 to 729.
It is 8 to 729. Is that going to reduce at all? No. I can tell you that it's not. And I can tell you that it's not because I know where it came from. How did we get 8?
Because
The
it's
volume of the
the
small
volume.
cube.
It is the volume. How did you get there? What did you physically do? What mathematical operation did you perform to get 8?
Base times height.
I suppose you did multiplication.
Area of the base times height.
Okay. I think you just cubed the lengths. Can we read that? Okay. So if figures are similar, and I should write that. And I should say objects, because these have to be three-dimensional things to have a volume. If objects are similar, then this last theorem, the final theorem of the year, then the ratio of lengths cubed is equal to the ratio of their volumes. Not a whole lot of fanfare for the final theorem of the year. I've had to watch Max and make sure that he blinks occasionally so that I know that we have a live picture of him. As excited? I mean, we started the year how long ago with, if two angles are right, then they are congruent. And we finally ended with, if two figures or objects are similar, then the ratio of their lengths cubed equals the ratio of their volumes. You guys do not seem appropriately excited by this.
I'm not.
Okay, thank you, Chesney. Thank you. At least warming my heart a little bit, making me feel good. And that's it. That was it. That is the year. That is everything that I have to teach you. Any questions on any of this stuff?
I'm assuming all of it or most of it is going to be on the final.
Yes. Any of this stuff should be on the final. So news about the final. We, as in the Geometry 9 teachers, me, Mr. Pavich, the coolest teacher that you guys didn't have, sorry, and Mr. Ross, who's also pretty dang cool. I am the black sheep of this group. The three of us don't want to give
way.
a final. We don't. We are, however, going to, we're required to do something. We are looking into giving a final project. The last I heard when we floated this by, the administration was kind of hemming and hawing over it a little bit. You know, they're like, well, it's weird that the Geo 9 students will be doing something different than the Geo students. We, as people who are good at proving things, however, pointed out the kind of error in that logic, that you are obviously going to be doing something different than the other Geo students because they're taking a different final anyway every year. It's not like we give the same final to all the different levels. So that seems like a good solution. We are conversing about it and working on it. Mr. Pavich and I started at 3 a.m. This fine morning exchanging emails. You might have noticed that all of you in this little picture thing received 2 emails from me this morning, at least 2 emails from me this morning, one around the 5:30 mark, one around the 7:30 mark. Telling you guys how you did on the test and all that. If you want a breakdown of your individual problems, how you did on each particular problem, I can send that information as well. Although some people have already asked for it and perhaps it wasn't that legible, I can do a little bit better and try that one again. But as I said, these things are in the works. So I am hoping that we don't have a final for you. Although it's kind of a shame, at the very beginning of this year, I went to Mr. Ross, who we have a yearly competition on whose class gets a higher average on the final. Okay? And it's largely multiple choice, just on the multiple choice section. So this is like no bias. We just run it through the machine. It goes, and it spits out a number. And I told him at the beginning of this year that there was no way he was going to beat me because I had a dang smart group this year. So I was looking forward to schooling one Mr. Ross, who, as I said, for the first time ever, someone beat me last year, and it was Mr. Ross. So sad for me. Okay, I am going to set up your homework for you on the hub so that you can hand it in on the hub this particular time around. And were there any questions on last night's homework? I'm going to turn off the recording.